Evaluating limits algebraically. Objectives. By the end of this lesson, you should be able to recognize when direct substitution yields indeterminate, list the indeterminate forms, evaluate limits using algebra. Past couple lessons, we talked about the substitution method, which worked for continuous functions. Right? For example, that's when I said, let's take the limit as x approaches 3 of something like x squared plus 2. Since this is a continuous function, all we have to do is substitution method. Just directly substitute it in. And you get 3 squared plus 2, which equals 9 plus 2, or 11. And that would be our limit. Right? Now that part of it's not going to change. Our first step is always just to plug it in directly. If you get an answer that works, you're good. But what happens when it doesn't work? What happens when we do it to a non-continuous function? So let's look at this example here. We want to evaluate the limit as x approaches 1 of x squared minus 1 over x minus 1. If we just look at this function a little more closely, first we notice if we're trying to graph or something, so we need a factor. So we have x minus 1, x plus 1 to the difference of 2 squares. For x minus 1, now the linear terms cancel out, and we get x plus 1. But we actually don't, this doesn't equal x plus 1, right? It equals x plus 1 with the whole. It's very different. This equals x plus 1 when x does not equal 1. It's a very different thing than them actually being directly equal. This function here equals this function when x does not equal 1. Very different. So that means that this graph is an x plus 1 graph with the hole in it. So if we notice that and we try to go, oh, let's do direct substitution, right? Let's plug in 1. If we plug in 1 originally, we're going to get this. 1 squared minus 1 over 1, which is 0. Now this is called indeterminate. We'll talk more about that later. But the general idea is that's undefined. So like, how do we find the limit of this guy? Well, let's look at this a little more closely. We're going to look at these two values here a little more closely. Well, first, let's just talk about how to find the limit of this guy, right? Let's try to find the limit of this guy as x approaches 1. We have a graph right here. Let's look at that guy. So, when we find the limit using a graph, we're going to look at both sides coming from the left. And coming from the left looks like we're going to get 2. And then coming from the right, looks like we're going to get 2. So the limit of this guy is just going to be 2. If we look at the graph of, right, what this is almost equivalent to is x plus 1. Same idea. Coming from both sides. Well, it is a continuous function, so it's just going to be 2 either way. So these values match here, right? These functions, this graph has a hole in it, you get the exact same limit. And that's what this lesson is going to be about. The way you find the limit of something that's not continuous, that has a hole in it, is you want to look at the function that's nearly equivalent to, that's like the nicer version of it. We're going to use algebra to get to that nicer version. Get to the nicer version. And then we can just use direct substitution. And that's what this lesson's about. Now there's one caveat, we can only do this when they're exactly the same except for at one point. But let's talk about that more in detail right now. Theorem. Let f of x equal g of x for all x not equal to c in an open interval containing c. So all they're saying is, hey, there's these two functions that are equal except for at one point c. Kind of like the example we just did. Right? These two functions here were exactly the same except for that one point at x equals 1. Where in one case we had a hole, in the other case it was filled in. So what this theorem says is that when you have that case, if one of those limits exists, then the other one exists, and more importantly, they're equal each other. Just like the second example we did, right? The limit here exists, the limit there exists, and they're both the same value. So that's what that theorem says. Now let's define indeterminate. We say that a function f of x has an indeterminate form at x equals c, or that f is indeterminate at x equals c if when f is evaluated at c we attain an expression of the form of these guys. So all this is saying is when we actually just sub it in, like if we try to do like the substitution method, and we get 0 over 0 or infinity over infinity, then these are called indeterminate. And all that means is we have to do more work. That's not an answer. We don't just stop at indeterminate. We don't just stop at infinity over infinity 0 over 0. That means we have to do more work. These are indeterminate forms, which means you're going to have to do algebra now. You're going to do more work to get the proper answer. Now, these are also indeterminate forms. These are ones we don't use as much. Infinity times 0 and infinity minus infinity. Those are also considered indeterminate forms, but in AP Calc, we really just focus on these. These are the ones that we really just focus on. that they're given to us. Let's look at 0, 0 real quick. If you remember back to our example, that's the indeterminate we got when we did the limit. When we did direct substitution with the limit as x approaches 1, and we plugged it in. We got 0 over 0. We got the indeterminate 0 over 0. So that means in this case we had to do more algebra. We had to factor and cancel out, and then we could plug it into our nice new function. And that's all this theorem says. So it says, hey, when it doesn't work the first time, you get indeterminate form, fix it first, and then try it again. So we're going to extend our substitution method for limits. We had this earlier in an earlier video, but now we're going to extend it. Right, so when we do substitution method for limits, step 1 is still the same. Just plug in the limit. That's all. That's what this says. If x is a continuous function, the limit is equal to the function value. So it's always the first thing we're going to do, just plug in the limit. If you get an answer that works, if you get like a number or something that works, you're done. That's your answer. Step 2, though, if you plug it in and you get an indeterminate, if you get 0 over 0, or infinity, or infinity minus infinity, or 0 times infinity, if you get indeterminate, then you fix it. You try some algebra step to fix it, and then you try to plug it in again to try to get to that function where it works, where it's nice, and then you can plug it in. So that's really the method. That's really the new substitution method for limits: is plug it in. If it works, you're done. Great. If it doesn't work, if you get indeterminate, 0 over 0, infinity over infinity, then do some algebra first, and then plug it in. That's really it. Now the algebra, though, that's where it gets tricky for some people. So let's talk about how to solve limits by using algebra manipulation. So there's generally 3 ways we're going to do it. So again, this is what we do after we plug it in. If we get an indeterminate form, then we're going to do some algebra. The first way, the most basic way, is to factor, expand, and cancel. The second way, we're going to multiply by the conjugate. Remember the conjugate, that's where if you have a plus b, you want to multiply by a minus b. That way, when you multiply them together, you get a difference of 2 squares. Right? That's the conjugate. That's where you multiply it, you change the middle sign, you multiply it, and that gives you a difference of 2 squares. It works for lots of things. It works for a minus rad b. Conjugate would be a plus rad b. Right? That's just the form. Change the middle sign, get 2 squares, that's the conjugate. And then some good old fraction and simplify. So let's go over an example of each one of these. Example. Find the limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3. So remember, the first thing we want to try is direct substitution. Just plug it in, substitute it in. If we do it here, this saves a little time, I just wrote it out right here. You get negative 3 squared plus negative 3 plus 6, and you get 0 over 0 indeterminate. Remember, all this means is you have to do more work. It's not an answer. That's supposed to work. It's not an answer. So, in this case, if you notice, this seems fairly easy to factor, so we're going to factor this. So let's factor this. Now, right here, I'm going to write an equivalent fraction, so I got to bring over the limit. You cannot drop the limit. So, we can make it a little nicer by just putting an L as limit as x approaches negative 3. Let's factor the top, so that'll be x plus 3, x minus 2 over x plus 3. And now, if you notice, the linear x plus 3's cancel, and we get the limit. Again, got to bring down the limit. You can just write L if you want, though, of x minus 2. And now we have 2, I said. And now we have a continuous function. So all we do here is direct substitute. We get negative 3 minus 2, which is negative 5. Keep in mind, just to reiterate, you have to bring the limits down. These two functions are not equivalent if you don't have the limit. As we talked about before, x plus 3, x minus 2 over x plus 3 does not equal x minus 2. It equals it when x does not equal negative 3, right? When it has a whole, they're the same. But by itself, it doesn't equal. So you can't just go, oh, this equals, you can't just go x plus 3, x minus 2 over x plus 3, and then go straight to x minus 2. These are not the same, right? Now, we can do it with the limits because of the theorem we talked about earlier. Right, this says if you have two functions that are almost equal, except for at a point, then the limits are equal. And that's why we could do it, right? Because these two functions are equal to each other except for at a point. So that's why you have to write down the limit. Otherwise, you get marked off. So just bring the limit down every single time. Once you get down to a continuous function, then you just plug it in. So let's do the next example. Now again, each one of these, you notice that I already filled in myself the first step, which is how do I find the limit of this thing? Step 1 is always direct substitute. See if you get an answer. If you get an answer that works, you're good. If you get indeterminate, you have to do more work. So for this problem, right, we have the limit as h approaches 0 of this monstrosity of h plus a squared minus a squared over h. First thing I did, I showed the work already, so I plugged in 0 to see if I got an answer, and I got 0 over 0, which tells me some stuff is like, okay, I gotta do some algebra now to fix this, because this is not a nice answer. It's not an answer. So let's do some algebra on this one. Now on this one, it's gonna get a little messy with the algebra. So it's gonna be a lot more straightforward than the last one. All I'm gonna do is this. Let's expand h plus a squared. We'll do it up here. H plus a squared. As you should all know, this is not h squared plus a squared. I would hate you if you do that. You just have to multiply by itself. Distribute. And you're going to get h squared plus ah. Anytime two variables, you're supposed to write alphabetically. Plus ah plus a squared. You add these up. H squared plus 2ah plus a squared. So that's what this part is. So let's rewrite this equation. So this equals the limit as h approaches 0. All this is now this h squared plus 2ah plus a squared and that is all of this part. I still have the minus a squared. On the bottom I have h. Now we gotta simplify a little bit more, right? I still cannot plug 0 and I'll still get 0 over 0. So let's simplify this top here. Now remember, parentheses don't really mean anything unless there's like a multiplication sign in front of the exponent. So in this case, it's like not having parentheses at all. So if you look at it, a squared minus a squared, those cancel out, and I'm just going to get this. Let's rewrite it in their equivalent limit. H squared plus 2ah, the a squares cancel, all over h. Now here, again, you could try plugging 0 to substitution. You're still going to get 0 plus 0 over 0 or 0 over 0. So you have to still do some more algebra. Here's a hint. Look at the top here. What do they share? An h. So we could factor out an h. So I'm going to write limit. Don't ever forget to write the limit. Factor out the h on top. You still have one h here. Over here you have no h's. Over h. And then the h's cancel out. Then I could write this as equivalent limit as h approaches 0 of h plus 2a. Remember, the whole goal of a limit is that you just want to plug it in. That's all you want to do. Only problem is if you get 0 over 0 or infinity over infinity, then you have to do some work. But once you get to that point where when you plug it in, you actually get something. In this case, I get 2a. That's your answer. My answer to this limit is 2a. Right? It's not 0 over 0. It's just a straight out answer. So that's it for that problem. So now let's move on to the next problem. Find the limit as square root of x plus 1 minus 1 over x. Now again, as I always say, step 1, direct substitute. So we're going to plug 0 in. Look what I did right here. You can see what happens. You just plug 0 in, you get square root of 0 plus 1 minus 1 over 0. Square root of 0 plus 1 is the square root of 1. Minus 1 is 0 over 0. So again, we have indeterminate. All that means is to do more work. Again, don't forget, step 1 is always direct substitute. Always. So let's talk about how to do more work on this one. This one we're going to do the conjugate. So the thing with this one is, if you look at it, right, I can't factor. I can't expand. That's why we have to use the conjugate. Because over here I have kind of the a minus b. So what I'm going to do is multiply both top and bottom. Because if you do conjugate, they'll both top and bottom, a plus b. So let's see how that works. So we're going to do the limit as h approaches 0 of square root of x plus 1 minus 1 over x. Let's multiply by the conjugate. So all I'm going to do is change the middle sign here. So square root of x plus 1 over square root of x plus 1 plus 1. So a couple hints here. When we multiply these, we don't have to simplify the bottom because we're going to want stuff to cancel out. So we're just going to keep the bottom like this. Write my equivalent function. Don't forget to write the limit. On the denominator, we're going to have it like this. Just leave it. Do not do more work for yourself. Don't expand it. Just leave it like that. On top, don't forget, this is the difference of two squares. This is a minus b and a plus b. If you can see that line green, I'm sorry about that. We should get a squared minus b squared. So in this case, I'm going to get the first thing squared, which is just going to be x plus 1. Right, when you square a square root, they cancel out. And then you're going to get minus the last thing squared, which is 1. If you simplify this, don't forget the limit. The 1's cancel, and I just get an x on top over x times square root of x plus 1 plus 1. If we simplify that, don't forget the limit. Look what cancels out here, the x's. Now, don't forget, when stuff cancels like this, the top doesn't go away. There's a 1 there. There's always a 1 there. Right? When stuff cancels, there's always a 1. So there's a 1 right there. And on the bottom, I have square root of x plus 1 plus 1. And now you got to a point where I would try plugging 0 in. See if it works. See if you get a number. Right? As long as you don't get 0 over 0 or infinity percent, you're good. Just plug in 0. I'm going to get 1 over square root of 0 plus 1, which is 1 over square root of 1 plus 1, which is 1 over 2. If you notice, I didn't put a limit here because I already plugged in my value, right? I didn't write down limits on these because once I substitute it in, it's no longer a limit, it's just a value. And I got 1/2. Let's do another one of these. Now that you understand the basics, I'm going to go a little faster here. So same idea here, find the limit of this, right? Remember, for step 1, plug it in. I plugged it in for us already. In this case, I got 1 over 0, which is, we consider that infinity. It's infinity form. And I got 4 over 0. So in general, when you divide by 0, you can't do it. So it's a form of infinity. So we get infinity over infinity. Just keep in mind, that's just like bad news. You can't divide by 0. So it's an infinity thing. So it's an indeterminate value. So how do we solve it? Do some math. In this case, we're just going to do common denominator. So I'm going to do something a little faster than normal. So let's factor the bottom here. X minus 2, x plus 2. If we're going to do common denominator, that means I'm going to multiply the right side by what's missing. In this case, we're missing x plus 2. So multiply both top and bottom by x plus 2. So if I did that, I'm going to get this. The limit as x approaches equals 2 of x plus 2 over x plus 2, x minus 2. Right, from this side, this side was missing x plus 2. Minus 4 over x minus 2, x plus 2. Now the other same denominator, we could add the tops. So I'm going to have the limit. Don't forget to write the limit. X plus 2 minus 4 is just going to be x minus 2 over bottom, which is, I'm just going to simplify x squared minus 4. And now if you want, again, you can plug 2 in again. We can always just plug 2 to see if it works. And in this case, we're still going to get an indeterminate form. So I still have more work to do. I'm not done yet. But if you notice, I can factor the bottom. So let's rewrite that. The limit as x approaches 2 of x minus 2 over x minus 2, x plus 2. X minus 2's cancel out. Don't forget when they cancel, there's always a 1. So you get the limit as x approaches 2 of 1 over x plus 2. And now, I think when I finally sub it in, it should give me a straight out answer. 1 over 4. So that's how that one works. Let's just do some more. This is fun. Next one, same idea. Let's take the limit of this thing. Oh, this one looks ugly, right? Of 1 over 3 minus 3 plus h over h. But don't forget, no matter how ugly it looks, the very first thing we always do is just sub in the value. So let's try that. You sub in the value. In this case, I do get 0 over 0, so an indeterminate. So to do more work. So in this one, the hint is we're going to combine fractions and simplify. It's going to be kind of like the last one, where the only thing I can really do is add fractions up here on the numerator. So we're going to find a common denominator. Right, we're going to multiply this left side by what's missing on the denominator right here, which is 3 plus h, 3 plus h. We're going to multiply this side by what's missing on the denominator on this side, which is 3 and 3. So multiply this side by 3 over 3. Multiply this side by 3 plus h over 3 plus h. So let me rewrite it. Don't forget to write the limit. I'm going to get 3 plus h over 3 times 3 plus h minus 3 over 3 plus h times 3 all over h. Now we can combine the numerators right here. Now in this case we don't have that problem, but a lot of times if I switch these, people always forget to distribute the negative. I like to do this so I know to distribute the negative. In this case it doesn't really matter because it's a single term on top. But if these guys were switched, it would matter a lot. That negative should distribute to both things. So I'm just going to simplify this thing real quick. The limit, don't forget it. 3 minus 3 cancel out. I get h over 3 times 3 plus h. Remember, you don't ever want to simplify the denominators. That's kind of the way it is. Over h right here. Now we have a complex fraction. And if you're in my class before, you know the key to the complex fraction is don't be lazy. This is a divide sign. All we're going to do is rewrite this. This is the limit as h approaches 0 of h over 3 plus h divided by h. Now you can go ahead and skip this step because we know what dividing means. It means multiply by reciprocal. So if you want, just skip that step and go straight to here. This is h times 3 plus h multiply by the reciprocal, and then these would cancel out because they match. And we have this limit. Sorry for all over the place right here. Of 1 over 3 times 3 plus h. Right? All I did was found the common denominator. Did that. This is my algebra, right? Cancel stuff out. I got to here, a complex fraction. Don't be lazy, just rewrite it. That's what that divide means. So I rewrote it, multiplied by reciprocal. I got this. Right, and then we get to the point where, hey, let's try plugging in, let's do direct substitution, plug it in. If I do that, I get 1 over 3 times 3 plus 0, and I get 1 over 9. And that's my answer, right? It's not indeterminate. Let's do one more of these. So last limit one we're going to do. So, example, find the limit as x approaches 0 of x 3x minus e to the x minus 1. Again, step 1. Plug in direct substitution. See if we get an answer. In this case, I get 0 over 0. So we have to do more work. Now again, this lesson's all about doing the ones that have more work. Sometimes, I mean, in real problems on the test, on the quiz, on the AP test, when you plug it in, it will work, and you'll be done. You don't have to do any more work. So don't forget that step. Don't lose easy points because you're so used to having to do all the extra work. So in this case, let's look at it. I guess you can multiply the conjugate. It's not going to help you. The easiest way to do this is just factor. There's ex's everywhere, especially on top here. These both have an ex. E to the 3x is just another way of writing ex times ex times ex. Because remember, when you multiply, all you're doing is adding the powers. X plus x plus x is 3x. So you can write it that way. Or in this case, when I factor out an ex, I'm going to get this. E to the 3x, remember when you factor, you're just dividing. What do? You subtract the powers and you get e 2x, right? Or that's it. You pull out an ex, there's only 2 of them left. You pull an ex from that one, you get a 1. And when you pull an ex out of this guy, there's a 1 left over. On the bottom, we have ex minus 1. Now know what you're thinking. Those guys don't cancel out. Oh, and also you're thinking, Fergosa, you forgot the limit. I know. It's bad. I'm sorry. Damn, I feel embarrassed. Anyway, we have this, but you notice these do not cancel out. But if you look at this guy, that's a difference of 2 squares. That's essentially a squared minus b squared. So we could factor this guy one more time. So bring it the limit as x approaches 0. Didn't forget it this time. I have ex. Let's factor this guy. That's going to be ex minus 1. Ex plus 1, right? Some real algebra stuff. the bottom we have EX minus 1. And now these cancel out. We have the limit as x approaches 0 of e to the x plus 1. Remember, there's a 1 on the bottom, but we don't have to write it because it's on the denominator. And then we just want to do direct substitution. So you get e to the 0, e to the 0 plus 1. Now don't go fast here. Don't forget, anything to the 0 power is actually 1. So the answer here is 1 times 1 plus 1, also known as 1 times 2, or just 2. So that's the answer to that one. And those are examples of how to do indeterminate forms. So a little quick summary, right? Don't forget, step 1 is to do direct substitution, right? This is always step 1. If you get a number that works, you are done. That's it. Direct substitute first step. If you get an answer that's not indeterminate, you are done. Other thing to keep in mind, people always mix these three things up. 0 over any number is 0, right? Come on, grade school stuff, right? 0 over 2, that's a 0. So that is this guy. That's an answer. If I said, what's the limit as x approaches 0 of x over 4 or 3, you would just get 0 over 3, which is 0. You are done. You got an answer. On the other hand, if you do direct substitution, you get a 0 on the bottom, right? We can't divide by 0. That means the limit does not exist. Why? Because that's what a vertical asymptote is. The infinite limit. Infinite limit is just a vertical asymptote, right? That's the whole point of the vertical asymptote. That's a one line you can't have a 0 on the bottom, so call it a vertical asymptote. So the limit does not exist. So if you get this, if you get a 0 on the bottom with a number on top, the limit does not exist. And then finally, if you get 0 over 0, that means you need to do more work, right? That's our indeterminate form. So this is a recap, right? 0 on top, it's like normal. 0 over 5 is a 0. 0 on bottom by itself, no other 0, that does not exist. You can't divide by 0. That's a vertical asymptote. And 0 over 0 means to do more work. It's called indeterminate form. And one final thing I do want to point out, as you kind of see by today, actually what a lot of people have a problem with, it's kind of a jokey thing, it's not like actual stats, but it's very true in my class. What people actually have problems with is algebra. Algebra is the most common mistake in calculus. It's actually just algebra mistakes. We'll get to chain rule, we'll get to integration, where you see, especially in chain rule, where people also make mistakes. But a lot of times, it's just the algebra. If you get your algebra sorted up, you can be fine. Don't make the silly mistakes.